So we're going to look at an application of derivatives. As a matter of fact, several applications of derivatives today. One of them is velocity and acceleration, but we will also look at some other applications as well. You know, we've already looked at velocity. On the first day, we looked at derivatives, right? We understood that, you know, when you look at the distance function, distance over time, and as you shrink the time interval, and as you're looking at ratio of, you know, how much distance has been traveled over how much time has elapsed, that ratio gives you distance over time average velocity, and in the long run, as you make the distance increment smaller and smaller, you have instantaneous velocity. We had already seen that. So if we assume that s of t is our distance function once again, the distance from the ground at any given time t, then we've already seen that s prime of t, which can also be written as ds over dt, the rate of change of distance per time, represents instantaneous velocity. And today it will be helpful to know the units for our, units will help us interpret certain derivatives. So for example, ds over dt, that's change in distance per unit change in time. ds also means like delta meaning a change. So can you tell me the units for ds over dt? So like what are the units for distance, change in distance? What are the units for that quantity? It depends, of course, whether things are in feet or meters or whatever. Let's just say some measurement of distance, say feet. And for time, let's say we have seconds. So what are the units for ds, dt, or s prime of t? Feet per second. This simple idea will help us interpret some other types of derivatives today. Just find the units first, and that will tell you what the derivative represents. In this case, feet per second or distance per time represents velocity. Okay, and how about, what if I take the derivative one more time? I take the derivative of the velocity function. Any ideas what that would be? The rate of change of velocity. What is that? Acceleration, right? So that is known as the second derivative of distance. So s double prime of t. So the first derivative of distance can also be written as v of t, velocity function. And then the second derivative of distance is known as the first derivative of velocity, or dv dt. That is given the name a of t, acceleration function, the rate of change of velocity. And today, basically, we're going to do some examples about this basic concept that s prime represents velocity, s double prime represents acceleration. We'll be doing some examples. And you have a handout with the problem now. Now that we know the shortcut rules, we can use them, and we can answer a wide range of questions with regard to the distance, the position, the velocity of this object. In this case, we have an object, a rock thrown from the surface of the moon, and s of t represents the height from the surface of the moon at any given moment as 24t minus 0.8t squared. Again, does everybody have this? Okay, the examples on one side of that sheet. Okay, in part A, we're asked to find the functions that represent the velocity and the acceleration for this function. So that should be pretty straightforward, right? What will be the distance function is given. What will be the velocity function? Again, velocity is instantaneous rate of change of distance, and we know that's the first derivative, right? So just find the first derivative of the distance function, s prime of t, in other words. So that will be 24 minus 1.6t. So instead of x, we have a t, but that's nothing new. We've even worked with a t at one point. And what about the acceleration function? Basically, just differentiate it one more time, the above quantity, right? So that'll be negative 1.6. And since everything was in terms of meters and seconds, the velocity of the function will be in terms of meter per second. and acceleration will be meter per second square. Because if you think about it, velocity is meter per second, and you're taking it with respect to t again, so it's meter per second, so that turns out to be meter per second squared. Okay, what about the part B, the height and velocity after 1 second the object was thrown in the air? So the height is the distance function, right? So s of t gives you height, but now we want 1 second later, so we want to find s of 1, distance 1 second after it was thrown. So we'll just plug in 1 into our equation. And let's see what we're getting. Is it 23.2? And the units would be meters for the, this is just distance from the ground, right? S of t is distance, so that will be just meters, right? They also want to know the velocity 1 second after it was thrown, so v of 1 equals, just plug in 1 into the velocity equation, so there we have 24 minus 1.6. And what do we get, 22.4? And what are the units? Meters per second. Okay. Now, the first two questions you could have answered without having, any new topics learned today. It's just very, very intuitive, I think. But the next one will make you think for a moment, perhaps, when does the object reach its maximum height? So an object is thrown in the air, it goes up to a certain point, and the gravity pulls it back, even though it's maybe lower gravity on the surface of the moon, it will still eventually come down. So the question is, it goes to a maximum height and starts returning back towards the surface of the moon. So the question is, when, at which moment, after how many seconds it was thrown, does it reach its maximum height? That's the question. And to answer this, we can actually take advantage of what we know about derivatives. So if we say that this is the this graph represents the distance of the object at any given time t. Because how did I know to graph a quadratic upside down like that? Well, I looked at s of t. S of t was a quadratic function, right? With a negative t squared term, right? That negative t squared term tells me it's going to look upside down, right? And how do I know where it's going to cross, that it's going to go through the origin? When t is 0, what was s of 0? If you plug in 0 into the original equation, s of 0 is 0. So it was thrown from the ground level, basically. Initial distance was 0. It wasn't thrown from a certain distance. So I knew that it was going to go through then the 0, 0 point. This is a very rough graph. When we're done, we can also check it on the calculator by putting the equation into our graphing calculator. But at the moment, it's enough to give me an idea about what's happening. And I need to know when it reaches the maximum height. What do I know about that moment? And this graph is your hint. At that moment, slope is 0. In other words, at that moment, when it reaches its maximum height, momentarily, the rate of change of distance is 0. It's increasing its distance. It's momentarily stops, and then it starts going the other way. The distance starts getting smaller, right? So at that moment, the instantaneous rate of change of distance is 0. The slope is 0. In other words, v of t at that moment momentarily is 0, right? So if you want to find out at what time that happens, we just need to set up a very simple equation. And the equation is set the velocity equation equal to 0, or set the derivative equal to 0, same thing. So our velocity equation was, so we're going to set s prime of t, or velocity, same thing, equal to 0. And we know that was 24 minus 1.6 t. So let's solve for t. And divide both sides by 1.6. And let's see what we're getting. Okay, did we get 15 and everything was, the time was in seconds, 15 seconds? So we're saying that this point right here should correspond to a time of 15 seconds. So 15 seconds after it was thrown in the air, we would expect it to reach its maximum height. Seconds. Any guesses then as to when it's going to hit the ground based on the graph? It's perfectly symmetrical in this case, right? Being a quadratic, you would expect it to hit the ground in 30 seconds. In a little bit, we will also do that with the analytical approach by solving an equation, but from the graph we can clearly see that. But I want to caution you, there are some examples in this section, like the very next one we're going to do, or some other ones as well. If it doesn't start at 0 point, maybe something like this. So the time to reach maximum height is not always going to be the double. You cannot always double it to find the time that it hits the ground, because you may not have perfectly symmetrical situations. This only works if it was thrown from a 0 level, from the ground level. Then you have a perfectly symmetrical graph. Then you double it to find the time it takes to reach the ground. But there is a question, I believe. Yes. Was there a question? You already got answered. Okay. So let's move on to part D. Part D was asking, what is the maximum height? So now you know when it reaches the maximum height at time equals to 15 seconds, right? But then the question is, what is the maximum height in meters? What is that distance? So how could I find that? Now that I know the time is 15 seconds, plug it into the derivative or the original? Into the original function, because distance is what we want to find here, right? So we need to know the distance from the ground at the moment when time equals 15 seconds. And let's see, what was my distance function? 24t minus 0.8t squared. And let's see what you all are getting for this. I heard 180. Anybody else who can confirm it? 180. And the units would be meters. So this point here now we know the answer is 180. Next question is, when does the object hit the ground? Now we already have guessed this one based on the graph, but remember I caution you, sometimes it is not going to be perfectly symmetrical, so it's important to know how would you do that analytically in case you don't have a symmetrical situation. How would you find when the object hits the ground? Which equation should we set? At the moment it hits the ground, what do we know? At this moment right here, the original distance from the ground is 0 right at that moment. So let's set the distance function, like I believe AJ suggested, set the original function, meaning the distance function, equal to 0. And Daniel, you had a question as well? Mm-hmm.
Yeah, the maximum, I got 5,000.
Okay, can I see maybe you entered something incorrect in the calculator? Oh, the first one should not be squared. It was just 24t, not t squared, yes. Mm-hmm. That sounded awfully high. So it's always good to question yourself if something doesn't make sense. So how are we going to find now the next one? What is the velocity of the object as it hits the ground? Now, of course, one moment after it hits the ground, the object stops. The velocity is 0, but it's coming down with an impact. It's coming down with a velocity, like it's hitting the ground with a velocity, basically. And what is that velocity? That's what we're trying to find. But first of all, I was about to show you part E with the analytical approach. We know the answer will be 30, but how do you do it by hand? Let's finish that one before we move on to F. So it was 24t minus 0.8t squared. We're going to set it equal to 0. Normally for quadratic equations, you may want to factor it. If it doesn't factor, and you will find that many of these are going to have messy numbers, then it's good to use the quadratic formula. But in this case, since the third term is missing, this is an easy quadratic, right? What can we do here to solve this one? Just take out a t, exactly. So now we have 24 minus 0.8t equals to 0. So either t is equal to 0, which we knew at that moment that distance was 0, or the other quantity, 24 minus 0.8t is 0. And in that case, t is equal to going to be 24 divided by 0.8. And that we expect to be 30. And indeed it is. So it hits the ground in 30 seconds. And finally, the velocity of the object as it hits the ground. The moment after it hits the ground, it will be 0, but it's coming down with a velocity. At any given moment, while it's up in the air, it has a velocity and hits the ground with a velocity. And once it hits the ground, it'll become 0. But with what velocity is it going to hit the ground, basically? How can we find it? What should we do? We know when it's going to happen, right? It's going to hit the ground in 30 seconds. So what should we do? Okay. Do we set equal to 30, or do we substitute 30 in for t? Exactly. Substitute 30 for t in the equation for velocity. So we want to do v of 30 seconds. What's the velocity at that moment? And we had already gotten the velocity equation. It was 24 minus 1.6t, and now t is 30. Okay, don't be surprised if you get a negative result. First of all, tell me the units, please. Meters per second. And the negative indicates, because velocity basically is technically a vector, it indicates direction and the magnitude. Speed, which is the absolute value of velocity, is always positive. Like if I said the speed, what's the speed? That would be 24. But the velocity, that means it's going at 24 meters per second, but it's headed downwards. That's why we're getting a negative as our answer for the velocity. And finally, in part G, we'll check our answers by graphing s of t on the calculator and checking some of the answers that we've already gotten. So let's do that. Let's go to our calculator and enter your y equals to s of t function into your graphing screen. So go to your y equals and go ahead and enter the function for the y equals screen. 24x minus 0.8x squared. Now when we graph it, if I just do zoom 6, which is like from negative 10 to 10, you will get like only a very tiny little bit of the graph. You don't even see it. It's going so steeply. But now that we've done the work, we can do an intelligent design in terms of like design your window carefully. Like now that we've seen the dimensions, what would be a better idea for our window? X is time, so we should start at 0, right? And X maximum, we know it's going to hit at 30 seconds. Why don't we make it like maybe 35 so we see where it hits and then maybe a little bit extra room left there. And for the Y, what do we know about the maximum height? I'm going to start at negative 5 because I want to see the x-axis there. For the maximum height, 200, because we know it's going to go as high as 180, right? So 200 would be a good idea, or anything higher than 180 is okay, 200. So again, you know, in hindsight, now that we've done the problem, it's so much easier to pick these values. If you haven't done the problem first, just keep increasing them, and if you don't see a good picture, go back and still basically do trial and error. But now we don't need trial and error because we know the answer for the maximum height, etc. So there's the perfect looking graph. And if you can trace this, of course, if we trace it, for example, I'm just going to press the button x equals 15 right now. So I did trace and I put 15. I want to see, okay, exactly in the middle there, when x is 15, y is 180, exactly like we got it. And of course, you can trace to see what's happening at 30 seconds. Just see that it's hitting the ground. And you can even check your derivative at that point. There is actually a numerical derivative option. If you go to second trace opens the calculations menu. Second trace. And I want to know what the derivative is, what the velocity is at that moment, okay? Because dy dx is going to be your rate of change of the function at the given moment. So pick number 6. Let's see, is it going to accept maybe a point? I'm going to put 30. So first I went to the menu. The second trace was calculations. Then I picked the dy dx command. Then while I was on the screen, I pressed 30 because I want to know the derivative exactly at 30 seconds. And I pressed enter. It gave me negative 24. Isn't that what we got for the last part of the question, right? Negative 24 meters per second. So that's something that we could check. But of course, I need to see all your work, all your analytical solutions. But it's a wonderful tool that you have that you will be able to check some of your work. And if you find that they're not matching, your answers are not matching to the graphing calculus answers, you have a chance to go back and fix your answers. Okay. Okay.